Okay, so in the first part of the video related to chapter 1 of class 11th, we introduced ourselves with physics, right? And here let us continue to the next topic. So here let us understand what do we mean by physical quantities. Okay, so this term in my explanation of how you are able to listen and see me, we have used few times. So let us start, digging a little deeper into it. Okay, and to put it, very simply. So in physics, we would continue our quest to observe, right? Learn, and when I say learn, we talk about doing the right measurement and correlations. Okay, apply those learnings, right, and evolve. So this is something which I call the Ole principle. Okay, so as a student of science, it's so this is not confined only to a discipline of physics. Probably you may use it in any faculty of science which you are studying in, or maybe if you like and you adopt it, probably you may adopt it in your personal or professional life as well. That's on to you. Okay, so this is what we would be doing throughout these studies. Okay, so physical quantities. So fundamentally, your physical quantities are those observable, measurable quantities using which we define the various laws of physics, right? How those physical quantities are connected, what would be the equations and things of that nature. Okay. While the example that I just quoted while explaining physics, as that deals basically with energy. Okay, the waveform of energy, be it sound energy or light energy, or for that matter even electrical energy, right? So at the end of the day, that is nothing but everything is nothing but an energy. Okay, let us take another example, the very famous example of how did Newton discover gravitation, right? So yeah, so an apple falls on his head and he ponders that, okay, why does everything fall down, why does it not go up, and he invents the law of gravitation over a long period of time, after doing a lot of measurements, after doing a lot of experimentations, and finally the theory of gravitation comes into picture, right? So, and when we are talking about theory of gravitation, the very basic physical quantity which is attached to explain that law would be mass, right? So an apple falls down, but something which is massless, it would not fall down because earth cannot exert the force of gravitation on that, right? So and that is why mass becomes a physical quantity. It's measurable, it's observable, and a law of physics, that is law of gravitation, can be explained using mass. But then, is it only mass which is involved? Probably not, right? Because we know the Newton's law of gravitation, that it is of F equal to gm1 m2 by r squared. So mass is involved, distance is involved, right? So when we say distance between those two particles, right? So these are some of the physical quantities which we have discussed in our last few minutes of discussion, and similarly in throughout the faculty of physics, there are a lot of physical quantities that we would come across. But again, as we talk about the law of correlation and unifications, right? So we would try to understand then that if we know about electrical energy, what similar things should be there in light energy, what similar things should be there in sound energy. So we would, once we understand one physical quantity, obviously we would try to coordinate things to another one, but whatever is possible, we'll be doing that. Okay, so physical quantities at a very high level, one of the ways of defining or describing them is fundamental physical quantities and derived physical quantities. Okay, so let us just write down the three physical quantities which we wrote on the board before a few minutes, right? So we had something called energy. So I would put energy here. Okay. Then we had mass. I will put mass here. I will put distance here. So here, being students of science, if you observe that fundamental physical quantities, just like letters A, B up to G of your alphabets in English literature, so these are the fundamental quantities with the meaning that they are, they have independent existence and they cannot be expressed in terms of any other physical quantity, right? Because if you need to write A, you have to choose this letter. You cannot do any magic from letters B to Z and write A. That's why A has a separate place in the alphabet, right? But if I want to write apple, all that I am doing is I brought in one A, two P, one L and one E, and this becomes a word. So similarly in physics, when we take the fundamental physical quantities and combine them, we get into the derived physical quantities. And if we can correlate between the beauty of literature and our physics, if you see here, letter A is used one time, 2 is 2 times, L is 1 time and E is 1 time. So the ground rule is how many times each letter needs to be repeated in a word. No one can have a rule defined for that. Similarly, physical quantities may be required to be multiplied multiple times to express a derived physical quantity, and we would get into more details of it in next few minutes. So let us understand that what are the fundamental physical quantities that scientists across the world have come together and agreed. Okay, so distance, we can rather say it also as length. Okay, and time. So these are the three very fundamental physical quantities that scientists across the world have agreed that using these three physical quantities, most of the physical quantities which we see in our day-to-day world can be explained. So let us see how we can explain energy in terms of mass, length and time, right? So energy, from your class 10 studies, you would have already understood that energy and work are interconvertible, right? So I can say energy is equivalent to work. There's a reason why I'm putting equivalent. We will get into the details later. Okay, so I can say this is nothing but your work. I can say force times distance or displacement. So right now I'm intentionally using few terms interchangeably. We will, as we move into next chapters, we would be using them more cautiously. Okay, force. Now force. What is the formula for force? We know from our class 10 studies. Mass times acceleration, right? So mass, acceleration, and then distance, right? So mass, I have already hit a fundamental physical quantity, so I cannot decompose it further. This is just like your letters of English alphabet, A, B, C, D, right? But this distance, this is again, I can call it as length, I need not change it. But acceleration, this I can further decompose. So let's do that. Mass, acceleration, we know this is nothing but your speed or velocity. So right now let me write speed for the ease of understanding. Speed per time, right? And distance, I can put it again as length, right? Now, if we go further, mass, fundamental physical quantity, speed, we can again say this is distance upon time divided by time into length, right? So what we are getting is mass, let me bring this length this side, length and another length. So I can say length to the power 2, this distance also I can say is length, okay? And then this time would come to the denominator, so it would be time squared. So if you see, we can say that energy is nothing but mass into length raised to the power 2, time raised to the power 2. So this is the fundamental reason why these quantities are called fundamental physical quantities, and there are a huge number of physical quantities which are your derived physical quantity. So in the interest of time, I would let you to explore, yourself by deriving the derived physical quantities and try to establish them or try to express them in terms of mass, length and time, okay, the fundamental physical quantities, okay. So I leave that on you. Now, when these three fundamental physical quantities were defined, slowly, as we saw and we talked about in my Ole principle, evolve is a very important phenomenon, right? So as physics evolved, as science evolved, many more disciplines got added to physics, and where these three physical quantities, mass, length and time, could successfully explain or help deriving most of the physical quantities in your linear mechanics and your linear mechanics part of your classical physics. There were definitely few more things which could not be defined by them, and then scientists came together and added 4 more things, right? So yeah, so now what are those 4 more things? So they added Kelvin. Okay, so let's say rather than saying Kelvin, let me say temperature. Okay, let me say electric current. Let me say your luminous intensity. Okay, luminous intensity and amount of substance. Okay, so initially there were 3, 4 more got added. Now these 3 plus 4, 7. These 7 are internationally accepted as 7 fundamental physical quantities, using which all physical quantities in this world can be defined and derived. So obviously you need temperature to when you get into the heat part of physics, right? So heat, a lot of physical quantities in heat would need this, right? Electric current, obviously related to your electrostatics, electrodynamics and things of that nature. Luminous intensity would be fundamentally on your light part of physics, and obviously amount of substance is very important when we talk about the nuclear physics or the molecular physics, or when if you first say you want to say about modern physics, right? So it will be very important during that. Now these 7 physical quantities together are defined in something called your SI unit, system of international system of units. I leave it as a task to you guys to go and find out what is the exact French abbreviation of this term SI units. But from an explanation perspective, these 7 physical quantities are accepted as fundamental physical quantities under the definition of SI units. Now, here I have been repeatedly using a different word called unit. Okay, let us go into that. I have been calling out a different term called unit, right? So let us just pause for a minute, and then we would obviously go into and talk about units of all these certain physical quantities. Okay. Before that, let us before that, let us just understand that these seven are defined in the SI units. So when we are saying SI units, let us see what are the corresponding units that internal system of units has accepted as units of measurement of those physical quantities. Okay, so for mass they have defined your meter. Okay, for length they have defined your kilometer. Okay, time, second, temperature, Kelvin, electric current, ampere, luminous intensity, candela, amount of substance, mole. Okay, so these are the fundamental units defined under your international system of units. And again, I leave it as a task for you guys to go ahead and read the definition of meter, kilometer, time, and all these seven units. We pretty well understand what is meter, what is centimeter, what is kilogram, and all. So I'm not going to define it again here. But then it's good to read the definitions in the right way. If you get a theoretical question in your exam, probably you can handle it using it, right? So yeah. Now let us take a quick pause, and rather before that, right? So let us talk about a couple of other your international system of units. Okay, so there are some other very famous ones. One is called as your MKS system, one is your CGS system, and one is your FPS system. So for these systems, predominantly they have defined mass, length, and time. So mass in MKS is your kilogram. Okay, in CGS it's gram, in FPS it's pound. Okay, similarly length, here it's kilometer, in CGS it's meter, in FPS it's foot. Okay, no, that should be foot. Okay, now time is universally accepted as second in all these three units. Okay, now while we are not defining these units very closely, but then let us concentrate on some of the common errors people use while expressing things in terms of these units. Okay, so let's get started. So let us understand the common errors which people do while expressing any physical quantity in terms of these units, right? So for example, I want you guys to choose which of these is correct. Say I'm saying 100 Newton, right? 100 newtons, 100 newtons, right? Or 100 Newton, or 100 newtons, 100 newtons, 100 and apostrophe s, right? So yeah, so these are some of the expressions which I can think of right away. So let us understand which one is correct, which one is not, and the reasoning behind that. And trust me, guys, it may sound that why are we spending a lot of time on this? But trust me, in my industry experience of 15 years, what I have seen specifically, there are few errors which are used so frequently even by engineers that may make you surprised. But then yes, that's a reality. So sometimes not concentrating on the basics would not be the right thing to do. Okay, so I would say that this one is correct, and then this one would be correct. This is wrong, 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 and this is wrong. Let's understand the reasons behind that. Okay, so the international convention says that when the unit is named after a scientist and you are writing it, though in English literature we start the first letter of a name with a caps, but here this is wrong. So technically, if we are writing the full name of the unit which is named after a scientist, then the first letter should be small. So that is why this is right and the corresponding one where it is in caps is wrong. Okay, next thing, 100 newtons, right? So while from a literature perspective or from a lexical definitions perspective, saying 3 seconds or 5 minutes could be 100% correct lexically, but then as per physics these are wrong, because what are they? They are unit, and unit cannot be made plural. So when we are saying 100 Newton, so this is the idea, guys. Any physical quantity is expressed in terms of some numerical value and unit. So this numerical value could be any number, and when we are saying this unit, this is one unit defined, right? So unit cannot be made plural, and this thing is called the magnitude, right? So few people say that this is magnitude, but that's wrong. That's the numerical exponent which is which when multiplied to the unit we get the magnitude, because magnitude is something which expresses a physical quantity. We'll talk more about magnitude a little later when we enter into scalars vectors. Okay, so yeah, so that's why this 100 newtons, as it is plural, it's wrong. Here the first letter is caps and it's plural, so these two reasons make it a wrong expression. NS, again, people have a habit of putting a plural, so while if it had been just expressed like this, it would have been correct, but as it is expressed like this is wrong. Alright, next, NS, yeah, this is another very common mistake which people do. We have a practice of putting periods when we are expressing a word in terms of a letter or two, so that's why somebody would have put the periods, but this is wrong. We are not supposed to put periods like this. So even if when we are saying you're suppose 10 AMU, you should write like this, atomic mass unit. This is right, and not A dot M dot U. This is wrong. Okay. Similarly, apostrophe S, obviously this is wrong. So I don't know why people do this, but yes, I've seen a lot of people use apostrophe S when they try to write plurals, right? So yeah, this is the basic mistakes that folks do while expressing a unit, right? Or probably I'll say the magnitude of a physical quantity. So that is what they do. Now let's move on to the next part and let us discuss about dimensions. Okay. And let us see the use of dimensional analysis. Okay, so for dimension, so remember guys, the dimension of the fundamental physical quantities are defined. So for your fundamental physical quantities, the dimensions are defined. So mass, we express it as m, length as l, time as t. For the simplicity, I'm not writing down it for the others. I leave that as a task for you guys to go ahead and see. So for example, temperature, people write theta and things of that nature. So I leave it on you. Current we can write amperes. So rest please explore. Okay. And here when we are talking about the derived physical quantities, so we started with energy, right? And energy, the final formula that we got was mass length squared by time squared, right? Or I can say mass to the power 1, length to the power 2, and time to the power minus 2, or m1, l2, t minus 2, or 1, 2, minus 2, when this is expressed in terms of your MLT, right? So now these 1, 2 and minus 2, these are called the dimensions of energy, and dimension we express it like this, that the power to which the fundamental physical quantities should be raised to express any other physical quantity. So when we are talking about the own physical quantities, obviously it would be your m1, l0, t0. Okay, so these two you may write, may not write, it's your call. So similarly for length, it will be mass 0, length 1, time 0. For time, mass 0, length 0, time 1, right? So this is it. So we will just quickly see one or two more derived quantities for which we will derive the dimension, okay, and then we will move forward. So let us derive the dimensions of your force, right? Force is nothing but, we know, this is mass times acceleration, right? So again, mass is a fundamental physical quantity, so I can say m to the power 1, and acceleration, I can say this is nothing but your distance per time squared, time squared, or I can say m to the power 1, m to the distance, so this is length, and that's why I'm saying this length to the power 1, and time to the power minus 2, which means 1, 1, minus 2 in terms of your MLT. So these would be the dimensions of force. So we can say force is nothing but MLT minus 2. Okay. So while I encourage you guys to derive some more physical the dimensions of some more physical quantities, let's move on to the next topic, where we would see the uses of dimensional analysis. Okay. So dimensional analysis is basically used for three main purposes. Okay, so the first one is based on something called principle of homogeneity. Okay, and principle of homogeneity is used to check whether an equation is dimensionally correct or not. Okay, what does it mean? So remember friends, we know that if I ask you 3 meter plus 5 meter equal to how much, you can very easily say me 8 meters. But if I ask 3 meter plus 10 liter equal to how much, I know none of us would be in a position to answer it. And the reason is over here, principle of homogeneity, that in a physical equation, the physical quantities that are separated from each other either by a plus or a minus sign, they must have same dimensions or homogeneous dimension. Only physical quantities with homogeneous dimensions can be added and subtracted. Otherwise, they can only be multiplied but not added and subtracted. So, if an equation is dimensionally incorrect, then it proves that that equation must be incorrect completely. However, the converse may not be true, that when an equation is dimensionally correct, it may still be incorrect in reality, but we can say that at least it is dimensionally correct or not. So for example, if you get a theoretical question that what are the uses of dimensional analysis, this should be your first point, and let us try to understand it with an example. So let us go with a very famous example which you would have studied in your class 10 studies also. So you have studied this equation, right? S equal to ut plus half at squared. So let us understand whether this equation is dimensionally correct or not. Okay. So let's, and how many physical quantities we have in it? 1, 2, 3, right? Because I said you dimensional physical quantities are separated from each other either by a plus sign or a minus sign, or obviously by your equal to sign, right? So what is the dimension of this first quantity, S? This is nothing but the displacement, right? So displacement is nothing but your length, right? So I can say this is length to the power 1. If it's length to the power 1, obviously mass is 0 and time is 0, right? So the left hand side is just L. Now let us see the physical quantities on the right hand side. Okay. So as I have less space here, let me just write it here that dimension of S is M0, L1, T0. Now let us find out the dimension of this term ut. Okay, dimension of ut. U is nothing but initial speed, right? So be it initial or or the speed at the end. At the end of the day, it's a speed. So it must be distance by time, right? Into we have got time, right? Solving it further, obviously these two get cancelled. So we have got S, which means this is again length. So which means I can write L to the power 1, M to the power 0, T to the power 0. So again, so this one is also same. So this is your dimension of ut comes out to be M0, L1, T0. Now let's go to the dimensions of at squared. Right? So acceleration is nothing but your velocity upon time, right, into t squared, or velocity we can say this is distance per time by time into time squared, or solving it further it becomes s by t squared into t squared. Obviously